Hello everyone. Today we'll talk about chapter 2, Observing the Sky, the Birth of Astronomy. In some sense, astronomy might be the oldest field of science because even before human civilization, people tend to observe the night sky. So today we'll look at when we look at the night sky, how it looks like, and the brief history of astronomy. Today, I may ask you for a moment, set aside the knowledge of the universe you already know, such as Earth is a planet, we all orbit around the sun. And let's start with the observing the sky. We'll use the software Stellarium to do a virtual observation. And you can see this is about my current location, how the tonight sky looks like. And of course, in this simulation, it gets rid of a lot of light pollution, so we can actually see a lot of stars. And so you can see that is how the night sky looks like, right? If you want, you can see a lot of constellations by connect lines between all the skies. Let's focus on how the star appears to move across a day and across the whole scale of a year. We can always fast forward the motion. Let's start with right after the sunset. You will see the star appear if you move through the whole night. You can see this star it's rotate, right? So, if you haven't learned about the heliocentric model, oh, you see there's a shooting star right there. You'll probably see that from your impression when you're observing the sky. Looks like Earth is at rest. Everything else is somehow move around the Earth. Let's go all the way from sunrise to sunset. You can see it's appear we all at rest, but the sun is somehow rotate around us, right? So that's observation from our perspective. Let's take a look at, let's take an observation about the yearly cycle. So we'll first look at how the star move across a year. So basically we'll set the time around a midnight, like 12 a.m. Let's go back all the way to maybe 2020 to look at how the celestial object, the stars, the planets move. Remember, that is like every night at 12 a.m., you take a picture and you put together. So that is not the motion over a day, but the motion over like a year, a different day at the same time. Okay. So you can see something similar. Over the years, the star also similarly rotate around the sky and rise on the east and set on the west, the similar as a daily cycle. So you can see from our observation of daily and a yearly motion of a star and the planets, it's not hard to, from our perspective, looks like everything is a fix on a sky like a dome and rotate around Earth. So that is not surprising why the early civilization think about the Earth is always stationary and everything else is rotate around the Earth. So just from our perspective, when we look at the sky above, it is very, very straightforward, or our impression is that looks like they're gonna be a dome, or we call celestial sphere. Stars seem to be on this sphere around the Earth, and with a day, with a year, they all rotate. Their motion is rotate around the Earth. So the celestial sphere, remember, it's not a real sphere, it's imaginary sphere. That is, it seems to be where the stars are on the sphere. And the celestial sphere is as similar as the Earth, so we actually will give it some definition of different location. So first, let's look at, we are in North America. So if you stand upright and if you look all the way down to the top, and the highest point we call is Dennis. And we have our horizon. Our horizon means any, so pretty much if the land is flat, it's basically on the same level of the land. That means anything below the horizon you cannot see. And you can only see things above the horizon. However, you know the North American is not North Pole. And to define some special location on the celestial sphere, we actually extend the idea of the poles of the Earth as well as the equator. Let's go ahead look at our 3D model of celestial sphere. So you can see this celestial sphere, we are something kind of in North American. So we actually look at the angle kind of this way. So you can see we can mark the celestial. If you look at this is the Earth, if you extend the Earth's North Pole all the way to intersect with celestial sphere, we have North Celestial Pole. If on the otherwise, you can find in a similar way how you can find South Celestial Pole. And if you expand Earth's equator to intersect with celestial sphere, you will find the celestial equator. So that is basically all the stars are fixed from our perspective when we observe on the Earth. Now you can see if we let the celestial sphere rotate, it will rotate about its rotational axis, which is line marked between North Celestial Pole and the South Celestial Pole, right? So that's going to be our perspective if we look from about the same latitude here on the US. Now let's move back to the observation use stellarium. If I mark the celestial equator lines, you can see if you look at the north, the cross point here is a star called Polaris, and which is also the direction of the North Celestial Pole. You can see if we look at the yearly motion, as we talked about, the sky looks like rotates around the celestial pole. If we look towards north, which is most likely when we live in northern hemisphere, it's the celestial North Pole. You can see that's also a reason why in the ancient time, people actually use some stars to navigate. Because if you look at, you are able to find the star called Polaris, you can see, which is very close to the celestial North Pole, and you will find that is the direction of north. So you can see Polaris is a very important, one of a very important star for people in ancient time to navigate. So how they locate Polaris? You may heard about the Big Bear and the Small Bear. The Polaris is right on the tip of the tail of a small bear. So if you found the Big Dipper, then go a little bit, you will find the Small Dipper. And that's also the reason why in past, without the technology, people actually use constellation and stars to navigate. So that is basically how the sky above us looks like. You can see that the sun is one of the stars. It also has its daily motion to rise from east and set to west, and also its yearly motion. And it will get higher when we're approaching summer and get lower when we're approaching winter. So if we mark the sun's path on the celestial sphere, we call this the red path here of the sun, we call it ecliptic. Though this is a line on the celestial sphere to mark the sun's yearly motion. Let's go back to Stellarium and go and mark the ecliptic line. So let's go ahead to look at how the sun actually moves. You can see here the sun actually follow a path which we call ecliptic. So that's basically mark the sun's location at noon on every day on the celestial sphere. And since we already talked about constellation a little bit on how in the past people use constellations. And you may heard about there is a lot of constellations. In total, there are actually about 88 constellations on the celestial sphere, which help us to divide the sphere into different regions. But you may know that there was 12 zodiac constellation. It's actually very special among these 88. The reason why they are special is that at a certain day, the constellation is actually with the sun. Let's go all the way to the real time. If we go to today, you can see the constellation with the sun today is actually Leo, the lion, and the crab, the Cancer, right? So you can see, if you remember, we talk about this line, the red line mark the path of sun, we call it ecliptic. If you count the constellation actually lying on this ecliptic line, it is all the constellation we know about zodiac. You have Gemini, Taurus, Aquarius, Virgo. If we start time a year early, you can see the sun is gradually go over all of those constellations. So you can see the constellation is also located on the path, describe the sun's path. That is the reason make those constellations very special. We actually choose those constellations as zodiac. It is pretty much how we can observe if we observe a night sky over a year. Now let's look at what theory or what prediction we can make by observing the night sky. And if you observe night after night, you probably come up with a theory that Earth is at rest. The rest of the star, the planet, the sun, the celestial object all go around the Earth. So that is basically the first theory describe, or first a model describe the motion of a celestial object, which is pretty straightforward. And if we follow the process of scientific method, we start with the observation, then we make prediction, and we come up with a theory. So that is how geocentric model developed. And there's another theory, or I would like to say contribution of Asian philosopher in Greek Rome, is about the shape of the earth. And I want you to set aside all the knowledge you have about the shape of the earth. If you step outside, look at the surrounding, it's not hard for you to get a conclusion that earth is flat. And if you maybe travel to another city and you look around, you get the same idea. And you have the same observation. Looks like the surface of earth is flat. And you can make a prediction using the observation that maybe you travel to a different city, you will still see the surface is flat. So that is why the shape of the earth at the very beginning, the ancient people think about the earth is flat. However, this Asian philosopher or scientists, they actually made some more observation. They actually found some phenomena or evidence against the theory that the earth is flat. I just want to give you two examples here. Is that you can see here during the lunar eclipse, the earth is on the way between the sun and the moon. So you can see, actually you can see the shadow of the earth cast on the moon. You can see, maybe here it's better, you can see the shadow of the earth is not flat, it's actually curved. So that is one of the observation that is against the flat earth model or theory. And another example is that if earth is flat, that means at the same time, doesn't matter which city, which location you are, the sunshine will actually shine at the surface of the earth at the same angle. However, the ancient philosopher, they actually do an experiment on the same day at noon. And one city, they see the sunlight can go all the way to a well. And therefore, that means at this city, the sunlight casts no shadow. However, if it travels a distant away to another city, on the same day and the same time, same day of the year at the same time, they actually observe that the sunlight actually make an angle, are able to cast a shadow of the columns. So you can imagine if the earth is flat, the sun will basically shine on the earth all at the same angle. So therefore, these two observations actually is against the flat earth model, which actually urgent the revise of the theory. And later on, that is one of the big contributions from ancient astronomy, that they realized the earth is round, is not flat. Now let's talk about geocentric model again. What is a phenomena actually make people in ancient times start to think about? Maybe geocentric model is not the true model describe how everything moves. And when you do observation, you will see almost all the stars except the sun. And they pretty much follow a very regular motion overnight and day by day, year by year. But the problem is that when you look at the motion of the planet, it exhibits some weird motion pattern. Let's take a look at Mars. You can see here's a Mars. I'm going to set a time around 10 p.m. during the night, and I'm going to observe Mars day by day across a year, 1 year or 2 years. You can see Mars at first is pretty much follow the same motion of the star. But about a certain time, it starts to go back. Let's go ahead and play it again so to make sure you can see it clearly. So you can see here, Mars is pretty much follow the motion of all the stars from east to west. But at a certain time of year, it starts to going back, right? And then keep moving. So this is what we call the retrograde motion of the planet. Now let's get rid of the ground. And let's look at our other planet. You can see this marks the Sun, Venus, Mars, Mercury, Jupiter. I think Saturn is here. Okay. And we'll also observe across year to see what's the differences of the planet's motion compared to the rest of the stars. If we go that, you can see the stars as a background. They pretty much form a certain pattern. You can see there's one object always move very fast, which is the moon. You can see the moon definitely not follow the motion of other star. And now let's look at the planets. Let's look at this Mercury, right, which is a planet. You can see the Mercury sometimes appear larger, sometimes smaller, and it's not exactly follow the pattern of other stars, like Venus, as well as Jupiter and Mars. Those planets actually puzzle the ancient people who observe the night sky with a geocentric model a lot. Geocentric model seem to explain the motion of the stars very well, but it has actually have a hard time explain the motion of the planet. Like why some planets not follow the same direction, why they have retrograde motion. Like we talk about like Mars, Mercury and Venus, they keep moving one direction and later on they go back. Then they turn around again and keep moving, go back to the original direction. The motion of the planet really gave a hard time to a geocentric model. The ancient observers sometimes call theirs sky wanderer because it looks like they get lost when they move in the night sky. To account for the motion of the planet, Ptolemy actually revised the geocentric model to make sure it can explain the motion of the planet. And so if you look at the retrograde motion, it looks like those planets go around the Earth, but at the same time follow a smaller circle around itself. So therefore, this model is still geocentric model. The Earth is still at the center. They put a lot of what we call epicircle to account for the retrograde motion of a planet. You can see here this simulation will show you if you still put the Earth at the center, here's the Sun, and here's the Mars, how this epicircle can explain why sometime during the year the planets will go back and then turn around and keep moving. So you can see for this epicycle model, the Ptolemaic model to describe the motion of the planet, you will have a lot of little circles around the big circles. It's too complicated. When the model gets too complicated, it will basically inspire people or make people think about maybe the geocentric model at first is not the correct model to describe the motion of the object. The difficulty to explain a lot of phenomena using geocentric model actually lead to the birth of the modern astronomy. The most big contribution is from Copernicus. He proposed a heliocentric model. The main idea of a heliocentric model is that you can see helio is just means the sun. Earth is a planet. All planets circle around the sun. Only the moon orbits the Earth. So the stars, they are pretty much very further away from the sun. So therefore, they pretty much follow the same pattern of motion compared to the nearby objects. And the apparent rotation of the celestial sphere, the stars and the sun around the Earth, is actually due to the Earth's rotation. Our rotation of Earth itself is not due to the rotation of the rest of the celestial sphere. And finally, the retrograde motion, the weird motion path of the planets, is due to the Earth's motion around the sun. The Copernicus actually come up with a theory, but himself does not really carry out the experiment to test those theory. Let's take a look at how the heliocentric model explains the retrograde motion of planets. We will take Mars, for example. You can see in the simulation, we know the Mars actually orbits around the sun a little further than the Earth. We're looking at Mars just like you drive on the highway. You are in motion and look at our nearby cars. So at some time during the year, Earth is trying to catch up with Mars. So you can see. And once the Earth catch up with Mars, then you can see the Mars start to go towards opposite direction. As Earth keep moving, and you can see, looks like there's a one time the Mars turns around and keep moving with the same direction originally. So the retrograde motion can be simply explained by heliocentric model without introduce a lot of small circles. Copernicus is actually come up with a theory of heliocentric model. But around that time, there is not a trend to use experiment to test a theory. The great scientists who actually use experiment and observation to actually test or affirm Copernicus' heliocentric model is correct. Is another great scientist. You may also know about him, who is Galileo. I guess the famous story you heard about Galileo is that he dropped two balls with different mass on the Leaning Tower of Pisa, and the two spheres actually hit the ground at the same time. Now let's take a look at a video of a reproduce of Galileo's famous experiment actually on the moon.
We copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got
beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Proves that Mr. Galileo was correct in his findings.
And one big contribution of Galileo to astronomy is Galileo actually built his own telescope and made an observation to test the Copernican theory, the heliocentric model. One of the results of Galileo's finding is the phases of Venus, the similar as the phases of the moon. If you look at this picture, the phases of Venus can only explain using a heliocentric model. Some other big observation Galileo actually able to observe use his telescope is that he able to see the craters, mountains, and on the moon, and as well as there is a full moon of Jupiter revolving around Jupiter. If he observed that is actually some object revolving around Jupiter, that also indicates not everything is go revolve or go orbiting around the Earth. Now let's take a look at Venus in our virtual observatory of Stellarium. Let's get a little bit closer so we can see the face of Venus. You can see now the face is almost like a very thin crescent. So we'll fast in time to see how the Venus face change. You can see it's become now a thicker crescent, then it's moved to like a gibbous. And with time goes by, you will see the full face of the Venus. And if you keep moving, you can see now it's gibbous and return to the crescent. At the same time, the relative distance between Venus and Earth is actually changing. Sometimes closer, sometimes it's further. Let's go ahead and look at the four moons of Jupiter. We'll later on learn the four we call Galilean moon, which is the moon can be observed just use the level of the telescope Galilean built. It's Io, Europa, Ganymede, and Callisto. Let's go ahead and look at how the moon is actually go around Jupiter. You can see that if we just focus Jupiter, then you can see that is moon is actually rotates around the Jupiter. So which is exactly what Galileo actually observed. By the way, the bottom picture is the first set of telescope Galileo actually built to observe the night sky. And Galileo actually is a very great scientist, although he did not come up with a heliocentric model, but he actually opens the new way people can study the universe by use the telescope to doing the observation. With the help of the telescope, we're able to see things much clearer with more details. Even today, the primary tool we use to do the observation in astronomy is still telescope, which is date back to Galileo, who is the first person to point the telescope to the sky to do the observation. It is all about the chapter 2. In summary, in chapter 2, we talked about the observation of the sky above us and the birth of modern astronomy. We talked about celestial sphere, that is, the sphere stars seem to be fixed on around the Earth. We also talked about based on our observation of a night sky, or the ancient time, people observe the same night sky. They come up with geocentric model, and that is motion of the planet gave a hard time to the geocentric model, and later on Copernicus developed the heliocentric model, and Galileo is the first one used a telescope to make observation to test the heliocentric model.